everyone. This is Umair Durrani, and this is our very first episode of Transportation Talk under the Transportation Science Learning community. Today, we are welcoming Dr. Ayobami Adewale, who has a background in computer science, and he has recently completed his PhD in civil engineering with a focus on car following modeling using machine learning techniques. So welcome, Dr. Adewale. My first question for you is uh, why were you interested in doing transportation research?
Yeah, to be honest, I was mostly interested in autonomous vehicle, self-driving cars. So that was kind of like my first interest, trying to understand, uh, what's it called? Try to understand the whole mechanics about it. Then I got into understanding. For you to understand the driverless vehicle, then you need to actually understand human behavior, the human drivers, right? It's because for us to be able to create safe driving vehicles or safe driverless vehicles, we need to understand what is the current behavior of human drivers on our road, right? And that is kind of like embedded into transportation system, right? So that's how I kind of like got into it, from autonomous vehicle to understanding human driver behavior and back to autonomous vehicle. So yeah.
Right, great. Yeah, go ahead with your slides and let us know about what your research was like and what did you find?
Yeah, so today I'm going to just start off with car following behavior using machine learning model. And if we have time, we will get into some small code on how to kind of like develop, maybe build our first machine learning model. It could be very simple machine learning model.
Yeah,
So first off, I will just start off by talking about car following behavior. The concept of car following behavior is pretty simple. So the idea is that we have a lead vehicle in traffic, and we also have the following vehicle as well in traffic. And we kind of like believe, or the study is basically about that the following vehicle, these actually would kind of like, it's kind of like affected by the behavior of the lead vehicle. And when we talk about behavior, we're talking about the speed of the lead vehicle, and we're talking about the spacing between these two entities. So, for example, if we are in traffic, we have the following vehicle and we have a lead vehicle. If the lead vehicle starts to increase the speed, it would automatically increase the spacing. And if the spacing increases, the psychology behavior of the driver is to basically increase its pace as well, it increases speed as well. So the idea or the logic behind that interaction is what we refer to as like the car following behavior. Another part of that is the lane changing behavior as well. So the lane changing behavior is like a subset of the car following behavior as well. The lane changing behavior is basically saying if a vehicle is on the current lane and it's about to switch to a new lane, in this case, a target lane, then it has to consider different factors. It has to consider uh, the spacing between the two vehicles that it's about to encroach on, and basically the encroachment value here, which basically are kind of like psychological. And the study of that behavior is what we refer to as like the lane changing behavior, trying to understand what does the driver factor in before changing a lane. So that's the idea or the whole concept behind car following behavior and the lane changing behavior. And the next question might be, why are we kind of like interested in this behavior, or why do we want to predict this behavior, right? So it's kind of like important for us to understand this behavior because we can kind of like use it to assess the impact of changes in traffic. We can also use that behavior to kind of like model the road geometry as transportation stakeholders. We can also use that to kind of like model different variables, like for example, increasing or decreasing the posted speed limits on a road segment. So we can use those values to kind of like say, okay, if we understand the human behavior on a given segment, on a given road segment, we can kind of make different transportation decision and say, okay, based on what we've studied on this road segment, the drivers are more or less kind of like aggressive drivers, right? It could be due to the fact that the speed limit is high, and that's why we have a lot of aggressive drivers. So the decision could be like, okay, let's reduce the speed limit, right? It could be also that the speed limit is kind of like slow, and that's why low, and that's why we have like increased traffic volume. What about if we kind of like increase the speed limit? So the studying of that car following behavior can give us insights into different factors like into different transportation decisions, like for example, increasing the speed limits or whatnot, right? Also, predicting the human driving behavior would also allow us, like I mentioned initially, also allow us to develop or build safer or safe driverless vehicle. Because if we are able to understand or predict driver behavior correctly, then we are able to model better driverless vehicle. And that's why we're kind of like interested in that.
One
Uh,
question here
yeah,
before you go to the next
yeah,
slide,
for
sorry.
sure.
So eventually, when there is 100% autonomous vehicles on the road, we don't know when that is going to happen,
Mhm.
but whenever that does, at that point, driver behavior would be irrelevant. So people who are researching driver behavior now, do you think there's a relevance to driver behavior in autonomous vehicle research until we get to the point of 100% penetration rate?
Obviously, yeah, well, there's always opportunity to that, even if we get into 100%, what's it called, penetration rate. Because right now we are trying to reach 100%, right? And for us to reach 100%, we need to understand the current behavior of humans, right? And even after we reach 100%, right? So, for example, we have, let's say, we have different autonomous vehicles. We have Tesla, right? We have Waymo, right? And we also have, let's say, for example, Toyota trying to reach maybe level 3, level 5 autonomous vehicles, right? Even at the end of the day, when we get to this different 100%, we would have different driverless vehicles that have different configurations, right? Different, let's say, for example, safe speed or whatnot, right? So at the end of the day, even if we get to this 100%, we need to still understand the different variables that are being configured by different manufacturers, right? And for that, understanding different variables, we would need to also continue to optimize on those variables. We need to 100% continue to, what's it called, improve on those variables. So even if we get to the 100%, there's still room for improvement to get perfect or to continue reduce collision rates, because we would never get to, let's say, for example, 0% collision rate. But the aim is to always try to get to the point, get to a level that we are close to 0% collision rate. So even if we get to 100% penetration rate, we have different manufacturers who still need to kind of like need to optimize for safety, need to currently optimize for even comfort while considering different factors, basically.
Thank you.
Yeah.
Please proceed.
All right. So yeah, so how to predict driver behavior? So driver behavior models can predict movement of individual vehicles and their interactions, just like as we mentioned. So we have models can be assessed to kind of like predict how fast will a vehicle travel given different constraints. We could also have how closely will a vehicle follow another vehicle given a road segment, right? Given the speed of the lead vehicle, how closely will it follow it? We try to understand that as well. So when a driver can brake or accelerate, so we have different thresholds that different drivers are willing to accept, right? So we need to understand that, and we also need to kind of like break those levels into, let's say, for example, aggressive drivers would have drivers are willing to accept minimal or bigger risk. So these as well is kind of like important for us. How vehicles react at intersections. So we could have how road geometry affect drivers. So we could have, okay, some drivers are willing to increase their speed while going down the slope, while some drivers are kind of like cautious and try to reduce their speed by going down a slope. So these as well is what we try to understand. And predicting these, we have two approaches. So we have the mathematical physics-based approach, and we have the data learning or the data-driven approach. So data-driven approach, we call these ML or machine learning approach, machine learning. And in the case of theory-driven models or mathematical physics-based models, is basically mathematical models that relies on theoretical basis, right? On physical theory basis. And what do we mean by that? An example is the case of we have two drivers. We have the following vehicle F, and we have the lead vehicle here, right? We have some theoretical based model that says, okay, if the space between these continues to reduce, right? If the space between these two drivers continue to reduce, right? Then the following vehicle continues to reduce its speed as well, just because he or she is trying to avoid a collision, right? And we have and another type of that is as well is if if the following vehicle F and the lead vehicle starts to increase in speed, right? And the following vehicle is moving on a constant speed, then the spacing between these two entities starts to also increase, right? So we have different mathematical models that are kind of like based on these simple mathematical concepts or simple theoretical concepts. Then here we have the data-driven models that are basically kind of like saying we have a lot of data, we have the data, and there is a pattern in this data, and we can kind of like figure out the pattern and build a relationship between the following vehicle and the lead vehicle without actually being limited to a specific constraint. So in the mathematical model, example of this mathematical model is, let's say, for example, Gibbs. We have the Gibbs model that basically predicts the speed at t+1, right? Based on factors like the maximum acceleration rate, the maximum deceleration rate, the safe spacing, etc. Right? In the case of data-driven model just says, give me the variables or the data set that you have, and I will try to figure out a pattern in this data set that's able to predict, let's say, for example, the speed at t+1 or the acceleration at t+1. So in the case of data-driven model, we don't know the equation we are trying to develop. We just know there's a data and there's a pattern. In the case of data-driven model, we know the equation we're trying to develop. We need to fine-tune maybe the parameters, and we can kind of like use constant parameters. So in the case of data-driven, it would be more or less like, in the case of theory-driven, let's say we have, for example, the Gibbs model, and the Gibbs model doesn't currently consider the weather constraints, how it affects driver behavior. So for example, what we mean by that is that we have different kind of subset of weather conditions. We have snowy weather, we have sunny, and we have rainy weather conditions, right? The Gibbs model doesn't factor these attributes into how it affects driver behavior. So exactly why we want to develop a new theoretical driven model that's based on weather conditions and also uses Gibbs model. For us to do that, we need to kind of like go through different approaches, like coming up with the equation, validating the equation, and computing the stability of that equation if it actually works. In the case of data-driven model, all we need to do is answer the question of, do we have the weather condition, the data related to weather condition? Do we have the data related to the road segment, and do we have the data related to the lead vehicle and other attributes we are interested in? Then we can just basically pass that into our model without really wondering about coming up with a new equation. We'll let the data-driven model handle coming up with the equation. So what does that look like? So in the case of data-driven model, this is what it looks like. We have our unknown target. In this case, we don't know the function that we are trying to develop, right? What we know is that we have the example data set, which could have the speed, the spacing, weather condition, etc., right? Then we have our learning model, which could be Helen machine learning model, and it has infinite subsets of functions that's able to predict, let's say, the final speed. So it could have, let's say, 1 million possible subsets of equations that could calculate this speed, right? So the learning model tries to figure out which model is able to perfectly or close to accurately calculate the speed. And once it's figure that out, then it's going to give us, let's say, for example, we have 1 million functions, then it's going to return F100 and tell us, hey, after going through this data set, F100, function F100 was able to find the perfect pattern in the data set, and this is the function, and you can use this function or this model to predict afterward. So that's basically how the data-driven model works. And how do we predict using data-driven model? Just like I said, we could have something related to the leader speed. We could have something related to the spacing with the leader. We could have the speed difference. We could have the type of lead vehicle. We could also have, let's say, for example, the weather condition. We could also have, for example, we've had studies that said when in car following scenario, right, the following vehicle here is also affected by the following by the vehicle that's actually following it itself, right? So that could mean that okay, we have the data related to the following vehicle that's actually following the vehicle we are interested in. So in this case here, we could add another variable that says the following vehicles, the following vehicles speed, without wondering about creating a new model.
One question
Yeah.
about the hypothesis set part.
Yeah. Mhm.
Um, so you've shown us different F1, F2, these are functions.
Yeah.
So by these functions, do you mean these are individual models or are these individual algorithms?
These are not individual models. This is a single model, right, that we are training that has access to this function subset. So let's say, for example, uh, you are training, let's say, for example, a neural network, right?
Yeah,
When you are training a neural network at every step, right, it's adjusting its weight, right? And for every step that's adjusting its weight, right, this is F1. If it adjusts its weight again, the next function derived after it adjusts its weight is F2. If we adjust that weight again, the next function derived when it adjusts the weight is F3 until it gets to a point and says, I'm not able to adjust the weight further. And this is the final function, or this is the best model that I'm able to come up with. In this case, let's say it stopped at F5. So the function the model derives at this point here, function in this case is the weight derived by this model here at function f5 is the best model or the best function in its subset that it has found so far. So the learning model here is a single model, but the function here is possible functions that it can use to calculate, let's say, for example, the speed. But the function it returns to the user, which is G here, is the best function from its subset.
great. So the best function that you've gotten so far, you mentioned the word subset. By subset, do you mean it's just one trajectory or is it including multiple vehicles?
It's basically multiple vehicles, not just one trajectory. It's
Okay,
multiple
thank you.
vehicles. Yeah. So, oh, sorry. So, moving forward, we'll talk about human driving vehicles, which we've kind of like spoken about. How to we kind of like use scaffolding behavior to understand uh, how we how the interaction works, right? And one of the things we found in our research by creating models for calculating or predicting scaffolding behavior is in this case here. In this case here, we found that human drivers keep a short spacing with a lead self-driving vehicle than a lead human driving vehicle. And this basically means that the human driver trusts the self-driving vehicle more than it actually trusts a human driver. So in this case here, understanding this behavior here could basically means that human driver, human drivers have started to basically trust self-driving vehicle, or have started to accept that self-driving vehicles or driverless vehicles are now safer than human-driven vehicles. And that's why the human-driven vehicle in our own use case here was able to maintain low spacing compared to maintaining an high spacing here. That's basically an example there. So in the case of data-driven model, we have different data-driven model that you can use to predict scaffolding behavior. We have the random forest, we have the gradient boost model, we have the neural network, we have the LSTM, we have the GNN, which is basically the graph neural network. And you have different models like that, right? And the selection of model basically depends on the kind of problem you're trying to solve, the kind of computation power you have access to train this model, and the kind of data sets you have, right? So the kind of data sets you have, the computation power you have access to, and the kind of problem you are trying to solve will basically determine which model you want to pick up. So an example with the random forest, you see a lot of papers using random forest to predict car following behavior, but the focus is not basically to predict. The focus is basically to understand how variables used in the prediction actually interact with each other. The random forest is able to give us that by providing and telling us, oh, okay, the spacing or the speed or the weather condition actually influences the car following behavior more than another variable in the subset. And we also have the XGBoost model, which is kind of like a very good model, fast, doesn't need a lot of computational power, and it's good with big data sets. So let's say, for example, I don't have a lot of computational power, then I want to go with XGBoost. Then in the case of neural network is kind of like a complex network that we use. If you have access to computational power, you have a very large data set, then you want to use neural network. In the case of car following behavior, or in our own transportation, where we are dealing with time series data sets, most times you would see most research are using LSTM, and that's because it's perfect for time series data set. So instead of using plain neural network model, if you are working with car following model data, and you have access to computational power, and you have a big data set, so instead of using neural network, then you want to use, let's say, for example, the long short-term memory, because it's perfect for time series data. And in our own case, the car following or the trajectory data set that we have is a time series data. And what we mean by time series data is basically means that if we have an observation at t, right, the observation at t was actually influenced by the observation at t minus 1. So that's what we mean by time series data set. And the observation at t plus 1 could be influenced by the observation at t minus 1, and at t minus 2. Right, so that's what we mean by time series data set. And the long LSTM model is able to model that correctly and able to find that interaction between them. So if we take a look at, yeah.
Sorry, could you show us an example if you have data like that at your end right now?
Yeah, I can. Just give me. Yeah, so I have these data sets here. So this is an example data set that I created it like some minutes ago. So for me, I always use Google Colab, and that's because it allows me to offset. It doesn't limit me to what's it called? Doesn't limit me to a specific computational power. So with Google Colab, I'm able to kind of like I have access to different what's it called, CPU power. I could use CPU, I could use GPU. I'm not limited to my laptop configuration. I could subscribe and basically have more access to different computational power. So for me, I always use this. And you can see here, I could decide to purchase additional computational units or compute units if I see that I actually need more data set. But I'm just going to close this. So I'm going to be using Python as example. And for me, when I'm working with Python, the first thing I do, I kind of like just import pandas as PD because it allows me to work with CSV dataset. And the next step is basically NumPy because it allows me to perform any metrics calculation or basically just clean up, work with array factor faster. And basically that's it. So for me, I can just run these. So these are the kind of like two important packages I have here. And this is kind of like connecting to an available compute unit, and that's why it's taking time. Once it's connected to an available compute unit, then I'm kind of like good to go. So just let's give it that like couple of seconds.
By the way, for your thesis, when you were fitting the models, did
Mhm.
you also use Colab for
Yeah,
that?
yeah, yeah, yeah. For my thesis, I use Google Colab. Okay. So this, well, so this is this, and I'm going to kind of like just connect these to my drive, my Google Drive, so that I'm able to have access to the data set as successfully connected to this. So I could basically just do the error. So pandas allows me to read a CSV. So I could do with CSV, the mountain drive, the name, uh, IE, and I believe example data set. So this might take some time because when you look at the size here, I should have information about the size somewhere. Yeah, so the size of the data set is like 111 megabyte. So now this is loaded. So I can basically just look at my data set and basically say columns. Uh, So in my data set, I can see by saying df.columns, I'm able to see all the columns in my data set. So in this case, this is the transportation trajectory data set. I have the road segments, the vehicle ID, the length of the vehicle, in this case, the following vehicle, the length of the lead vehicle. Here is the local time. That means the time that the data set was collected in, or the timestamp of each data set. Here is the follower vehicle ID, and here is the lead vehicle ID and different stuff. So we have the process speed here, which is basically means the speed of the vehicle, of the following vehicle. And we also have, I believe we should have the process speed here, which basically means the lead vehicle speed. And here, when we look at this data set, to be honest, I think we are only interested in interest codes that we are interested in. We're only interested in the segment ID, interested in the length of the vehicle, we're interested in the F process speed. So here as well, we're interested in the lead vehicle speed. And we could select one, which is the spacing here, spacing headway. We could also select the ID of the vehicle. I think we're interested in those as well. And we're also interested in the position of the vehicle. So yeah, process positions. So for me, I already know what the dataset does. So I have an idea of what I really need. Ideally, when you don't have the idea of the dataset, then you want to do like some form of data cleaning or form of data extraction. But this dataset here is already cleaned, it's already extracted, so I know whatever that is going on there, right? So for me, I can look at this dataset and basically say, for these columns, try to describe uh, the, oh, what? That's weird. Oh, okay. My bad. Mm, Am I missing something?
I
Okay, let
think
me just do
cell
this.
5 needs to be run again, and then it
Sorry?
should be okay. Cell number 5 should be run again, the previous one, then
Okay.
it should work.
Let me see. Okay, yeah, I think that works. Describe. Okay. Yeah. So basically, I could describe this. So it basically counts. It shows different statistics or metrics about the columns I'm interested in. For example, the mean, the STD, the mean, the minimum value, the max value, and the 25%, 50%, and 75% STD. Basically, moving forward. So here I can look at like the spacing. Here I can look at the spacing and see that the maximum spacing here is 123 meters. I can also look at like the minimum spacing here is 4.3 meters or 4.37 meters. So this is fine. There's no negative spacing. There's no zero spacing, or which could mean conflict. So from there, you can see that basically this means that the data set was basically clean. And if you look at the F process speed, you can see that the minimum here is 0, so basically means that the vehicle was at standstill. You can see that the maximum is 3.3, 33 meter per second. And here as well, you can take a look at the length of the vehicle. You can see like the minimum length is 3.3, basically saying it's a very small vehicle. And here we can see that the max, what's it called? The max length is basically 9.24. So from here, we can basically see what the distribution of the data set is. And just like I said, I know what the data set does, so I have an idea. So here I can basically segment each of the data sets into different segments. So I can have the segment ID, a following vehicle ID, and the lead vehicle ID. So in this case, I can group my data sets into different segments. I can create a group value here and say, okay, this data set is grouped by segment ID, grouped by the leader ID, and also the follower ID. So I can group my data set based on these and basically just, I think I'm missing something. So I need the looker time here actually. Because again, we're working with trajectory data sets. So we can look at these again and look at the looker time. So the max is 19.8, the minimum is 0, basically saying it's starting from 0. And it's basically saying the max is basically 19.85. So here we can look at the following vehicle ID and the segments, and we can try to kind of like sort our data based on the time series. Since it's time series, I want to sort our data by different intervals from t to t+1, t+2, t+3, t+4. And how we do that is basically doing this. We have bf dot sort values. So one thing I like about the Google Colab as well is I don't need to remember anything really. It basically tries to, it uses AI to autocomplete and be able to say, okay, this is what I'm looking for. So I can look at the group that the data set is related in and basically add my looker time to that. And one thing I want to do is I want to reset the index such that the previous index from here, from the data set, the previous index here doesn't influence the sorted index here. So now I can sort my data sets, and now my data set is sorted based on the local time, the segment ID, the leader, and followed by ID. So to proceed, I can calculate things that I'm interested in. For example, I'm interested in, let's say, for example, the speed difference between the following vehicle and the lead vehicle. So in this case, I can have speed difference and basically say the process speed process speed. I'm not interested in this. So I can calculate the speed difference and also add that as the variable. So when we are developing a machine learning model, we have two things we are interested in. We are interested in the input features, and we're also interested in the output features. And generally, what does that mean? The input features basically means what's it called? The independent variables or observation. So in this case, input features, for example, when you look at the concept of Gibbs, the input features for Gibbs is the speed at previous step interval, the spacing, and then it's able to calculate the speed. But in the case of machine learning as well, we have that concept of input features. That means which features do we have access to? And the output feature is basically telling us the dependent variable, or in this case, what's it called? The variable that we want to predict. So here we have the input features, independent variables that are going to the model, and the output features is basically what we are trying to predict. In our own case here, what we want to predict is the speed at t plus 1 using speed at t, right? So we want to use the speed at the current interval. We want to use it to predict the speed at t plus 1 at the next interval. So now what we can do is that we can create our features, input features, call this the input features, create a new array of our input features and say we want to use the length. We want to use, let's say, the process speed, right? And we want to use, let's say, the space headway. Let's say we want to use the space headway. Let's use the popular terms that have been used by other mathematical model. So we can use the F process speed as well. So in this case, we've determined that we want to use the features. We want to use the following features as our input model. So I can compile these.
Can we also use speed difference?
It depends. I can decide not to use speed difference, right? So it depends. Right. So in this case, I don't want to use speed difference, right? I just want to use the process speed, right? And I want to use
one more clarifying question about the prediction time. So you mentioned t plus 1. Generally, for example, for Gibbs model that you mentioned, there will be a reaction time parameter that is used. So it would be t plus that reaction time, for example, 0.5 seconds, 0.3 seconds. So how do you determine what should be used here? Should it always be t plus 1 in machine learning models, or can it be different?
It depends on the observation of the data set. So for example, in our own data sets here, right? If I remember correctly, the observation was done in 0.1 second, right? So in this case here, let's say, for example, I've defined my next speed. So let's say in this case, I have speed, let's call this speed to predict, right? So the speed to predict in this case is this. So I can do something like the group by, is that correct? Yeah, I think it's group by. Is that correct? Yeah, group by. I can group by the keys I've specified, the F process speed, and basically do something like this, shift -1, right? So what this shift -1 does is that I'm predicting, so in this case here, I'm predicting the next speed, the F process speed at the next time interval. So in this case, t plus the local time observation, right? In this case here, I said the step in our local time for this particular data set is 0 plus 1, right? So let's say, for example, now our use case here, if I stick with this, our use case here will be t plus 0 plus 1, right? I can decide to say these actually want to shift these n minus 10, right? So that means what I'm trying to predict is t plus 1, right? I can decide to say I want to shift these to -5. Then that basically means what I'm trying to predict is 0 plus 5, right? So it basically determines on what it basically depends on what's it called, what the problem statement is. With machine learning, you have the flexibility of selecting what that t plus 1 is for you. And the data set also depends on what that t plus 1 is. So for example, let's say my data set right now is, instead of 0.1 second interval, it's actually 1 second interval. Then I need to stick with the 1 second time step. I can only increase by 1 second or by 1 second interval. But in the case of these data sets here, it's kind of like 0.1, then it gives me opportunity to be able to skip by 0.1 second interval. So, but in most trajectory data sets, the observation is always in 0.1 seconds interval, and that gives us the opportunity to be able to do all those things you mentioned.
Okay,
Does that
great.
make sense?
So yeah, thank
Yeah.
you. So we now have the features that you identified, and you've also created a speed to predict column.
Yeah,
Are we
exactly.
now ready to fit the model?
Yeah. I think we are ready to build the model. So we can go ahead and basically, oh, okay. Yeah, I knew something was wrong there. So let's see. Oh, sorry. Exactly. So now we have this, but one thing I always love to check is I try to check what's the length of the data set I have. So in this case here, we have 292,000 plus rows. And one thing we want to do as well is, since we've shifted these by -1, it's likely we would have empty sets because we've shifted the data upward a little bit. So we would have empty sets. The next thing we want to do is basically drop the values. And before we drop them, we can also try to specify what our targets or value to predict is. So in this case, the column we want to predict is this. Then now we need to clean up our data set and basically try to drop off any empty data we have. So in this case, we can do something like this, dff.drop empty data. Then we can have the subset equals the features, basically the features that we're interested in here. Then we can have the targets that I want to predict here, and that's it. Oh, what's wrong? Oh, my bad. So
Another question about the
yeah,
data format
yeah,
for building the model. Um, you have shifted the speed column by
yeah,
zero point 0.1 seconds, so we
yeah,
now have that as a target.
yeah,
But we also know that since this is sequential data, one trajectory's data ends and then another trajectory's data starts. So when we do that shift, is that taking care of these individual groups or
yeah. Because what we did was that we grouped by this,
yeah,
by the group we've specified here, right? So we are not just shifting for the sake of shifting, right? We are shifting based on the groups we've defined here. So when the shift
right.
happens, it basically shifts by this, and if it ends, it starts a new shift by the case, right? So let's say in this case here, I've specified this, I remove the group, right? Then that means at this point here, I'm not considering the group I'm shifting by, right? So it will just shift
Okay.
and continue to shift. But in this case here, I've specified the group. So that means it's going to shift considering this group. And once this group ends, it resets the shift again for the next group. So that's basically what happens there.
Okay. So after that shift, now the very first row that we have has
Mhm.
missing data for the speed to predict column, right?
Yeah,
Because we have
exactly.
shifted it.
Yeah, exactly. Yeah,
Okay,
exactly.
thank you.
Yeah. So now we have our new data, including everything we have, which is this. But one thing we always love to do in machine learning is we love to keep a subset of the data set, a subset that's never been seen before, so that we can use that to test the model. So in this case here, I'm going to create a subset randomly. So what I'm going to do is I'm going to create the test data. I'm going to call it the test data. I'm going to call this the model data or the model DF. And here I'm going to just pick sequentially, and I'm going to pick the first 20,000 rows as the test set. And the model data that I'm using for the model, I'm going to pick uh, the next 20,000 to the end. Oh, sorry, this should be new data. So I'm going to pick from these to the end, from 0 to 100 index, I'm going to pick as the test data. From 20,000 to the end, I'm going to use that as the model data. So now I can always work with the model def and just keep the test data for the future. So here now I can, what's it called? Create my X. In this case, I can call this, in this case, our input feature, and basically do this, right? So you could see the Google Colab already knew what I was trying to do. So here we have our futures, and here X and Y is basically the value we want to predict. So I can run this. And so right now I have my X, I have my Y. So there's something in machine learning as well that we call the test data and the train data, right? So the test data here is kind of like a little bit different from the test data here. So the train data here is what we use to train the model, and the test data here is what we use to validate the performance of the model or measure the performance of the model. And the test data here is what we use basically to say, okay, the model hasn't seen this data before. Can you simulate what's happening in this data? And we can use it to compare the performance of, eventually validate the behavior of that model. So for us to split our data into test and train data, in Python, we have the concept called train test split. So here we have train test split, right? So here we pass our training data, we pass the Y data, which basically value we want to predict, and we specify the size of the data. In this case here, we can decide we want to use 0.25. So in this case here, what we mean by 0.25 is that it's going to use 25% of the data as the test set, and it's going to use 75% of the data to train the model. Then in this case here, we have a shuffle flag. So like I mentioned, so since this is a time series data set, we don't want to shuffle the data. We want to keep the order of the data or the trajectory order of the data. So in this case, if let's say, for example, our data set is not a time series data set, then we can set this to true. And that means the train test split will just shuffle the split. But in this case, we don't want to shuffle the split. We want to maintain that, right? There are different ways of doing the split as well. We have something called the time series split as well. The time series split as well, which basically splits it based on the time series in the data. And we also have something called the group split. So that means it makes sure a specific group is in the training and a specific group is in the test data. So in this case here, I can have X train, which basically means the features used for training, and I can have the X test used for testing. I can have the Y train, and I can have the Y test here. And here, I have an error here. Test. Okay, so I need to import these function. So exactly. So these, I should be good to go here. So I can run these.
One clarifying question about this split. When you are doing this for 75%, it's going to be in our training set. Is there a chance that when it makes the split, it also splits a trajectory in the middle? Or would it take care of a complete trajectory goes in the train set and no part of it goes to the test set?
Yeah, we can do that. So in this case here, so what we've done here is that, so what we've guaranteed here is that the test is not shuffled, right? So that's what we've guaranteed here. But however, what still happens here is what you mentioned. Basically, what happens here is that we can still have a subset belonging to a specific group still end up in the train data, right? At least for the last 25% of the subset, right? We can still have that subset cause that. In this case here, we know we call something the group shuffle fleet. So we have a concept called the group shuffle fleet, which basically makes sure that the group we've defined here, right? The group we defined here is used to kind of like split the data. So that's what the group shuffle fleet would basically do. And how do we do that? We can basically do something like this. This is just an example. I won't be using this. So we can basically do something like this. We can create what's it called? We can create a pair ID, a new column called a pair ID, right? In this case here, we then have the group shuffle fleet. Then in the group shuffle fleet, not group shuffle fleet. We need to specify the pair ID first. So in this case, we call these the group we've defined up there. Then we kind of like create a pair ID of those group. So in this case here, this completes it for me. So we have these. And now we can create a shuffle split. Number of splits here we're interested in here is 1. So here we don't want a random state. We want you to maintain that. So here we can have these. I need to import the group shuffle fleet as well. So here we can have these. And now I can create the different indexes based on the pairs. I believe. Yeah. So here now, I've created a split that would make sure that what happens here doesn't happen here. So this would ensure that a specific group is in a given group, and the other group is in the test set. So this group shuffle split ensures that the splits are kind of like in the perfect group. So there's also something called the time series as well, the time series split, which is often used for LSTM. So what happens is that it creates different groups. So we can have group 1, group 2, right? So it's going to train on group 1 and it's going to train on group 2. Then the next thing happens is that it's going to create another group 1, group 2, and it's going to create group 3. So it's going to test on these and train on these. In the next iteration, is going to test on these. It's going to train on group 1 and group 2 and test on group 3. The next iteration is going to test on group 1, group 2, group 3, and test on group 4, right? So that makes sure that we end up coming up with a split that's basically time series.
The last one that you explained, is that the time series split?
Sorry?
The last one that you explained, was that time series split?
Yeah, that's the time series split.
Okay, thank you.
If I'm not mistaken, yeah.
I think in the interest of time, why don't you just now explain to us the machine learning model and what kind of results you got compared to traditional models? I know we don't have time left for the complete coding part.
Yeah, for sure. So let's see.
If you have remaining slides, you can use them.
Yeah. So, okay. Yeah. So I'm just going to skip through this a little bit. So we have case study 1. So one of the research I worked on was to kind of like develop a machine learning model and a physics-based model. So here we have an LSTM model. Just like I said, I'm able to use LSTM model because I'm using Google Colab, and I'm not limited to to computational power. So I'm able to use LSTM, and LSTM is basically a time series model that's powerful enough and is based on memory. So the memory opportunity allows the model to use memory and remember the previous value it's seen before. And it also makes use of some gating techniques, which allows it to ignore things in its memory that are not relevant to the next time step prediction. So in our own case here, we wanted to predict what's it called? The vehicle speed at t plus one using the vehicles using different values or attributes or features at t. So in this case here, we use the spacing, we use the speed of the lead and the following vehicle speed, and we also used something called PT, in this case, the prospect theorem, right? So here you can see that what we've done is not just using machine learning model, we actually compared combined machine learning model and physics-based model. And here what that means, what we are trying to do here is that in the case of machine learning model, we try to just predict, find patterns. There is no physics laws into the pattern. It just basically tries to find pattern in the data set. But in the case of combining both machine learning and physics-based model, we can try to include a form of, we can try to add the physics-based model as a pattern to learn by the machine learning model. So in this case here, what we added into the machine learning model is another pattern to learn, which is based on a physics-based model. In this case here, it's called the prospect theorem. It's trying to measure the willingness of a vehicle to cooperate with the lead vehicle. So that's what we try to use PT model or PT theorem to model. So in that case here, we just consider that as another input into the LSTM model. So now we have 4 inputs. We have the PT, we have the lead vehicle and following vehicle, and we have the spacing, and we can predict the speed. So in this case, we had to train our model, and we used 2 hidden layers here. And in those hidden layers, we had 100 nodes and we had 60 nodes respectively. We have the learning rate of the model here, we specified 0.01. We have the activation function, which we used here as ReLU. So the ReLU or activation function is basically used to introduce non-linearity into a machine learning model. And the batch size or the epoch size here, we used epoch size of 10. So that means 10 iterations. And the batch size here is basically 100. So that means we are considering 10, 100 trajectories at once when we are predicting or measuring performance of the prediction. Then we have the training algorithm here we use is Adam, and the time step here is 1 second. So in the previous example that I was trying to show, we're using 0.1 second. But in real world, it's kind of like too small to use 0.1 second. So here we use 1 second. So here we have the plot of the model, and we have 2 different subsets. We have AV following HDV, and we have HDV following AV. So we try to predict the behavior of an AV when it's following an HDV, and we try to predict the behavior of an HDV when it's following an AV. So in this case here, this is our PTLSTM. So you can see this is our PTLSTM in green, which is kind of like closely a little bit related to the observed variable, right? And we have the Gibbs model, which is basically a physics-based model, and we have LSTM, which is the lead vehicle, and we have what else we have? We have the PT IDM, which is basically these here. So in the case of our model, we were able to show that our PT LSTM or our PT LSTM is able to observe one. At t minus 1, what's most important is the following vehicles, the what's it called? What's most important is the the the, the following vehicle speed at t minus 1, right? And we can see that the trend basically continues to t minus 10, right? So at t minus 10, the speed of the following vehicle was still very, very kind of like important to predicting the speed at the current time step. But here, when we look at the order, we can see that the UT value, which is basically a prospect theorem, was only significant at t plus t minus 10, and it wasn't basically considered at the next time space. So in this case here, our observation or our willingness to cooperate was actually significant at t minus 10, but it wasn't significant at t minus 1. And we can also see that the lead vehicle speed was most significant at t minus 1 compared to at t minus 10. So that basically means that at previous time interval, it wasn't basically interested. It basically says, I'm just going to react to the speed because I have time to react at 1 second. So at this point here, it's considered the speed of the lead vehicle. And we can also see the trend here, the trend here, and the trend here as well. When we look at the spacing, we can see that the spacing is no longer relevant at this point here, but the spacing was most relevant at t minus 5 and at t minus 6. But make sure that at this time step here, this is at 0.1 second time space. So when we say t minus 10, we are not referring to what's it called? We are referring to t minus 10 times 0.1. So in this case here, this is 1 second. So at 1 second, it's kind of like important, the willingness to cooperate. But at 10 minus, at 0.1 second, then now it's considered the speed at the previous time interval. But here, this is the point we are kind of like interested in. The chart here is what we are interested basically in. And here we can see that the target speed, the order is the target speed is important. The willingness to cooperate is important. Then the spacing, and after that, does it consider the lead vehicle? And that's because the willingness to cooperate is kind of like easy to measure. The spacing is visual, it's easy to measure. That's kind of like what's it called? Might not be easy to measure for a driver that is driving. So here we can see that the values we have are very, very important, and we can kind of like look at a different time step.
Yeah, actually, it's a bit basic, rudimentary question.
Mhm.
What do you have to say about the generalizability of these models? Uh, because generally, let's take the example of linear regression. So we will say that our linear regression model, will predict only the things that are like really relevant to that scenario. So like the way I'm thinking about it is that we will need a new model for every situation, for every road segment. This way we will end up with thousands of new models. So what do you have to say about the generalizability?
So, ideally, to be honest, generability of a model of machine learning model is kind of like important, and it's one of the things that is being studied as well. But when you also say that, what's it called? We would always have to develop a new model every time. To be honest, that isn't necessarily true, right? So if you develop a model, we can say we want to develop a model for. We don't have to develop a new model every damn time, right? But because if we have like a large data set, right, that's able to capture scenarios that always happen, then that's fine, right? So in my own case here, I have, let's say, for example, 220 rows of data set, right? And in that case, here, 220,000 rows of data set. And in this case here, each rows or each time step is 0.1, right? In this use case, the generalizability of the model I generate from here would be inconsequentially low, right? Because if I take it to a different segment, I don't expect that model to perform as best as possible because it's basically just learning from the pattern within its dataset or within its use case, right? But when you look at, for example, um, taking a different segment, right? When you look at, for example, LLMs, right? When you look at large language models, right? You hear that we have billion weights that have been generated to train that particular model, right? And in that billion way, that means we have billions of terabytes or billions of data sets that have been used to train that model, right? And that's why you have different versions of, let's say, GPT-1, GPT-2, GPT-3, GPT-4, right? Because we are trying to improve those models one step at a time. So in the case of my use case here, if eventually we have access to billions of data set and we're able to train a single model to do that, then eventually we wouldn't need what's it called? A single data set. I'm sorry, we wouldn't need to generate different models for every use case. But in our own case here, unfortunately, we would always often have to generate a new model to predict or to address our very own use case. So an example of this case is, let's say I have 220,000 rows. In this case, it is Wemo dataset. I don't expect that the model I train a Wemo dataset on would actually give me a good what's it called, a good model when I use that same model to predict data related to or trajectory related to the NGSIM dataset. And that's when the generalizability of the model comes in, right? And if we look at physics-based model as well, right? If I what's it called? If I estimate the Gibbs model coefficient or estimate Gibbs model values based on Wemo dataset, right? I still need to fine-tune the Gibbs model variables to be able to accommodate NGSIM as well, right?
Yeah, that's
So
correct. Yeah.
so we would always often have the generalizability issue, but the moment we start to increase the availability of datasets, that generalizability would continue to improve as well. That makes sense?
Yeah, so this means that if we have large enough data sets and they are also representative of uh, n number of conditions, for example, different driving cultures, different
Exactly.
uh, hours of different like peak hours or non-rush hours and weather conditions. So if we train a like let's say hypothetically we have a rich enough data set and we train one model on that data set, then we will be able to say that okay, this model is universal in this scenario, if my
Uh,
question makes sense.
exactly, for that particular environment. So, for example, let's say
Yeah,
I
but
train a model with data specifically generated in India, for example, right?
mm,
I can't use that model, right, in, let's say, in Los Angeles, for example, right? Because these are different driving culture, and the model basically learned that culture from the data that it was given. So, but if we are able to merge the data set from those two entities, then we are able to generate a model that's able to generalize to those two specific conditions.
right. Okay, thank you.
Yeah.
If you know of any open source repositories or any source where we could find models that we can use, machine learning models particularly, I think there are trajectory data sets that are available publicly, but are there models, code that is available publicly that we can look into?
Uh, to be honest, um, to be honest, I think in the case of models, I think there's kind of like gatekeeping in the case of model, at least in transportation. I haven't really seen a lot of models in that regard. But nowadays, I think it's easier to even create models. To be honest, I think it's not even about creating models, about explaining what the model is actually doing, right? Because you could see here, I could generate a code with AI that's able to generate the model for me, but it's basically just explaining what that model actually does. So I don't think the model is actually it's about discussing the open source for models, but open source for data. I think that's one thing we need to focus on. How do we get better data that we can use in developing different models? And for that, for me, I always go to universities, the different universities, for example, maybe in Europe, and try to see what they are currently doing. An example of that is, let's say, this. This is a computer vision TUM School of Computation. Yeah, I think this is in Germany or whatnot, right? So I try to kind of like see what they are doing, for example, from their AI lecture series, and try to see what they are basically kind of like doing. For example, learning geometric structures. How does that influence the model I'm developing? So that's the way I generally just go about it. Look at universities in Europe. An example as well is I always kind of like go to Waymo, for example, and see what they are currently doing. This is a good repository as well. Exploring the Waymo open data set, it kind of like gives you an understanding into how to work with a data set. Because like I said, developing the model isn't kind of like the big thing, but working with the data set is the big deal. An example as well, I think, is the OpenAC trajectory repo or something like that. Yeah, so here as well, this is an open source as well. So here you can see like how to work with different data sets, how to clean up the data set, and how to kind of like maybe develop a model. So yeah.